A very common exercise in basic economics is to try to predict or understand what is the effect of a change in what is called a deep parameter in the economy, something like a change in the cost functions or the production functions, or a change in the tastes of the consumers. Such an exercise is called a comparative statics exercise. And if you want to understand the term, you just notice that what we want to understand is how the equilibrium price changes before and after the change. The general form of this exercise looks as follows. Let A be a parameter of interest. So it could be, for example, a parameter that indexes the technology state that we care about, or the weather, or something like that. And then what we can write is the demand function for every consumer as a function of P and the parameter A. We can model how that parameter changes the demand function, the same thing for every firm. And from that, we can compute the aggregate demand function as a function of the price and the parameter A, the aggregate supply function as a function of P and A. We equate them and we get the equilibrium price as a function of the parameter, and the equilibrium quantity also as a function, total production as a function of the parameter, or more generally, the equilibrium allocation. We care about other details of the allocation as a function of the parameter. And when we're interested in a comparative static exercise, for example, is saying if you're at initial value of A and A increases, what will happen to prices and to the allocation? That's the general abstract notion of a comparative static exercise. Now let me derive a very useful formula for doing comparative statics. We know that at equilibrium, and regardless of the value of the parameter A, the following has to be true. The quantity demanded in the aggregate at the price PA, given that the parameter is A, has to be equal to the quantity supplied at the price, equilibrium price PA, comma A. Please don't be confused by the notation. This is the equilibrium price as a function of A, and A is just a parameter that may enter and affect directly where the demand, aggregate demand and aggregate supply curves are. Now, what we can do is take the derivative on both sides of the equation to get the following. So this implies that the derivative of xd with respect to the P times the derivative of P star with respect to A plus the derivative of xd with respect to A, we have to derive it with respect to both things because there are two variables, is going to be equal to the derivative of xs with respect to quantity supply with respect to P times the derivative of P star with respect to A by the chain rule, plus again the derivative of xs, the quantity supply, with respect to A. And by doing a little bit of algebra, this implies that the derivative of P star with respect to A is equal to the ratio of two things, the derivative of the quantity supply with respect to A minus the derivative of the quantity demanded with respect to A, divided by the derivative of the quantity demanded with respect to P minus the derivative of the quantity supplied with respect to P. Now notice a couple of things. First is that for this mathematics to go through, we have to be at an interior solution where everything is continuous and differentiable, so you cannot really apply this at corner solutions. The second thing is that I claim that this is always going to be a negative term in any equilibrium of interest, and let's see why. By the law of demand, we know that this is either 0 or negative, and we've also seen that the supply function is either 0 or positive. So unless both things are flat, the net thing here has to be negative, because it's negative minus positive negative, or if which one's 0, the same, one of them is 0, the same thing applies. This is quite useful because it says that the effect of increasing A by a marginal amount on the equilibrium price is going to depend on the difference on the marginal derivative of the effect of A on the supply and on the demand. Let's do some examples. I'm going to draw them here just to derive some intuition about how to apply this formula. So suppose, for example, that A increases the marginal costs but has no effect on the marginal benefits. What does that do? That implies that the supply curve goes down. At any price, the firms are less willing to supply. So that means that the supply with respect to A becomes negative. But what does that imply? Well, this is 0, this is negative, the denominator is negative. This implies that the price goes up. In other words, a parameter change, an increase of a parameter that increases marginal cost ends up increasing equilibrium prices. Let's look at another example. Suppose that we have an parameter A that is, it increases, so A decreases the marginal benefit. What does that imply? It implies that at any price, less is demanded. So this is a situation in which the partial derivative with respect to demand is also less than 0, but minus minus gives plus, divided by minus. This implies that the equilibrium price in this particular case falls. Now let's do a more interesting case in which A has two effects. It decreases marginal cost and it increases marginal benefits. Now this has the effect of increasing the supply, and this has the effect of increasing the demand. We know that that by itself is going to tend to decrease the prices by the inverse logic that we saw in this case, and the opposite here. So the question is, what is the net effect? The net effect, the net or the sign of dP star of A is going to be equal to minus the sign of dxs dA minus dx d with respect to A. In other words, if the effect on A in supply is greater than in demand, then the price will go down. If, on the other hand, the effect on demand is greater than the effect on supply, the price will go up. And if they are exactly the same, they balance each other, they will have no effect. So this formula, I hope you can see, is very useful because it allows you to compute, starting at interior equilibrium, what is the effect of a particular change in one parameter of the model on the equilibrium price. And obviously, once you know the change in the equilibrium price, you can back from the demand function and the supply function what is the change in the actual quantities traded. Let's do one simple example to see how we play with this formula, how to use it in practice. So suppose that you're in a market in which there are 10 consumers that have demand function xid of P equals to 10 A minus P, where A is the parameter of interest. And you have 10 firms that have a supply function equals to 10 AP. So notice that the parameter here affects both the consumer and the producer. Let's start by computing what is P star of A is given by the solution to aggregate demand is equal to aggregate supply, but aggregate demand is just going to be equal to the horizontal addition of 10 times this, which is 100A minus 10P, and aggregate supply is going to be given by the horizontal addition of this, which is just given by 100 AP. If you do the algebra, this implies that P of A, P star of A, is equal to 100A divided by 100A plus 10. Notice that this number is always less than 1 for any A greater than 0. Okay. Next, we want to know what happens to the price, the derivative of the price, equilibrium price with a function of A, but we know from the previous formula that the sign of dP star with respect to A is equal to the sign of ds to minus the sign of dxs with respect to A minus the effect of A on the demand. So what can we do? What we can have is that this is equal to minus the sign, and let's compute these partial derivatives. For the demand, this is just 100. Sorry, it's with respect to A. So this is just 100. For the, I'm sorry, I keep doing it wrong. First, we're going to do the supply, which is this side. With respect to A, this is just 100p. And for the demand, we get minus 100. Okay? But we know that P is less than 1, so that means that this term is going to be less than 0, and together this implies that the sign is positive, because this is negative, minus times negative, it gives you a positive sign. So we know that in this particular example, when we increase A, we are going to have an increase in the equilibrium price. And by the way, we didn't need to use the formula. If you plot this graph as a function of A, what you're going to get is something like this, approaching asymptotically 1, so it's always increasing. So we already knew this, but it's useful to show that the formula works to train our trust of the theory.